This lesson is about proofs, or at least an introduction to proofs. We're going to talk a little bit about shorthand, and then we're talking about proofs by deduction, proofs by equivalence, or proofs by definitions. So first of all, some shorthand. We have words like and, or, not, if, then, if and only if, which you should have learned in geometry. And is written this way for proofs. It's like an upside down V. Or is kind of like a V, and then not is a negation, is a negative sign with a little dash on it. If then is an arrow on an equal sign going to the right. If and only if, which we also write IFF sometimes, is a equal sign with arrows going both ways. We also sometimes called and a conjunction, or is called a disjunction. Not is a negation. If then is called an implication, so we might say such and such implies such and such. Or equivalence is the if and only if. I want to remind you that we've done symbols sort of like this with sets. We had this symbol, which was intersection, which also meant and we had this symbol, which was union, which also meant or. And so these were kind of like the letter U, only not quite. And these are kind of like the letter V, only not quite. But they basically say the same thing. This upside down V is intersection, well, and conjunction. And the regular V is like union or disjunction. And the rest of them hopefully are kind of familiar to you. When you have conditional statements, you have if, some hypothesis, let's call it A, then some conclusion, let's call it B. You would write that as A implies B, if A, then B. And then the converse of that would be, well, you switch them. If B, then A, or B implies A, that's the converse where you switch the order. The inverse of the original one, well, you just negate both of them. Not A implies not B. If not A, then not B. And the contrapositive, you negate and you switch them of the original one. So not B implies not A. If not B, then not A. Now, you also might remember that the converse and the inverse statements are equivalent statements. So if the converse is true, the inverse is automatically true. If the converse is false, the inverse is automatically false, and vice versa. And then the original and the contrapositive are also equivalent. If the original is true, then the contrapositive is automatically true. If the original is false, the contrapositive is automatically false, and vice versa. So let's do an example of proof by deduction, known also as a direct proof. So we want to prove that if x is less than -5, then x squared is greater than 25. So I'm going to start with x is less than -5, and I'm going to put in brackets here given. Don't always have to have the statements and reasons, but I'm going to do it this way for the first example anyway. Now, if x is less than -5, I'm going to absolute value both sides. Absolute value of x and absolute value of -5. Well, when I do that, then because x was less than a negative number, it's farther away from the origin. So absolute value of x is the distance from the origin. It's going to be greater than. This is the geometric definition or explanation, if you want, of absolute value. Okay, and therefore, of course, that means that absolute value of x is greater than 5. That's just evaluate absolute value of -5. Okay, so now what I'm going to do, I'm going to square both sides, and because we're dealing with positive numbers, when you square both sides, the inequality will not change, because squaring is just multiplying by itself, which means you're multiplying another positive number. Therefore, the inequality is not going to switch around. So I'm going to have absolute value of x squared is greater than 5 squared, and I'm going to call that square both sides. And now I want to remember that absolute value of x squared, well, absolute value just makes it positive, but when we're doing x squared, it's going to be positive anyway, or I guess 0 is a possibility, but that still, it's not going to change anything. So really, I could say just x squared is greater than, and I'm going to call this one 25. And that's because absolute value of x quantity squared is the same as just x squared. And that's what I was trying to get. X squared is greater than 25. And so I started here, I did some steps, and I wrote the reasons for it, and I answered my question. And so I can end my proof with a little box. So part B says, explain why the converse is not true. So the converse says, if x squared is greater than 25, then x is less than negative 5. So to prove that the converse is not true, I just need to find a number or find a value that would satisfy this but not satisfy this. So consider x equals 6. Therefore, x squared is 6 squared, which is greater than 25. But x, which is equal to 6, is greater than negative 5. So x is not less than negative 5. So that's why the converse is not true. And again, I can end with a little celebration box. Okay, let's do proof by equivalence. Now, proof by equivalence is essentially how you basically solve problems. You're solving an equation. There's technically a symbol that you're doing every time that you're not actually realizing that you're doing. But anyway, the statement is, if a squared equals b squared, then a equals b, or a equals negative b. So this is what we're trying to prove. So to prove by equivalence, you just start with the thing you're starting with. So a squared equals b squared. And then I'm going to put this equivalence symbol. Well, if a squared equals b squared, that just means that a squared minus b squared is equal to 0. I just set one side equal to 0. We don't usually write this symbol every time when we're solving an equation, but since it's a proof, this just means equivalence. This is the same as this. Now I can factor a squared minus b squared. A plus b, a minus b equals 0, and again, these are equivalent. Now I can set each of those equal to 0. A plus b equals 0, or a minus b equals 0. And again, these are equivalent statements. And now I can say, well, that means that a equals negative b, or a equals positive b by basically subtracting or adding b to both sides. And here's the equivalence. And that's basically the end of the proof, because that's exactly what we were trying to do. Now, I do want to point something out. You don't actually have to use these symbols if you don't want to. It was in the problem, so it doesn't hurt to have it at the end. But if you use the word or, it's okay. You could probably get away with not putting these symbols in either. I would like to see them because this is a proof, not just solving an equation. But I think you can probably get away with not writing them if you choose not to. So next we're going to talk about proof by definition. I want to remind you about a few definitions that might come in handy. So a rational number is a number which can be written as p over q, where p and q are integers, and of course q is not equal to 0, so this is a helpful thing to remember. And then I want to talk about integers that are even or odd, because those come in handy. So an integer n is even if you can write n equals 2 times k for some k in z. Now I want to show you another symbol that's not in the textbook, but I like to use the symbol that's a backwards capital E. It says there exists. So basically, instead of saying this, I could have written if there exists a k in z such that n equals 2k instead. Now, I'm perfectly happy with the way that the book has written it. It's perfectly okay, but I might get lazy and start writing it this way in the future, so just beware of that. Anyway, the key is an integer n is even if n equals 2 times k, where k is some integer. An integer n is odd if you first take an even number and then add 1, or subtract 1 for that matter. So n equals 2k plus 1 for some k in z. And an integer n is divisible by another integer m if n equals k times m for some k in z. So those might come in handy as well. I wanted to add a quick comment that will help you when you start making choices about consecutive whatever. So consecutive integers, consecutive even integers, consecutive odd integers. So consecutive means they're one after the other. So the obvious thing is if n is one of the integers, then the next one's n plus 1, the next one's n plus 2, etc. And that kind of thing is fine. But if you're clever, you will try to keep the numbers as small as possible. So instead of n plus 1, n plus 2, you'd use like n minus 1, n plus 1. And so the number in the middle, as much as possible, is going to be the basic one, the n. Instead of n plus 1 in the middle, you want to have n in the middle. Now, of course, it would have to have an odd number of these in order to make it work. But still, if you had 4 of these, you'd use n minus 1, n plus 1, n plus 2 instead of n plus 1, n plus 2, n plus 3. Same thing with consecutive even integers. Obviously, you have to have 2n, and then 2n plus 2, then 2n plus 4. But it might be more convenient to do 2n minus 2, 2n, and then 2n plus 2. It just makes the numbers that you have to work with a little bit easier. And for example, if you have to multiply these out, these become the difference of 2 squares, for example. Same thing for consecutive odd integers. 2n plus 1 would be the first odd integer, add another 2, so 2n plus 3, and then 2n plus 5, etc. Or you could do 2n minus 1, 2n plus 1, 2n plus 3. And if you had 4 consecutive odd integers, then 2n minus 3, 2n minus 1, 2n plus 1, 2n plus 3, those 4 are perfectly symmetrical. So again, you're trying to take advantage of the smaller numbers as much as possible. So we've done this one before, at least something like it, but I'm going to do it again. Prove that 0.13 repeating is an element of Q, and we're doing it by definition. So first of all, let x equals 0.13 repeating, which is equal to 0.13131313 dot dot dot. And then I'm going to multiply by 100. Therefore, 100x equals 13.13131313 dot dot dot. And now I'm going to subtract x and subtract 0.13131313 dot dot dot. So that's going to give me 99x equals 13, and I've gotten rid of the 0.13 repeating. And now I can divide both sides by 99 and say x equals 13 over 99, which is an element of Q by definition. And that's the end of that proof. Again, we were trying to do proof by definition, so I wrote by definition. The definition of a rational number is it can be written as a fraction using only integers. Okay, prove that the sum of 2 rational numbers is also a rational number. Now, when you're trying to prove something like this, you can't use specific examples. You have to make it generic. So I'm going to say let A, B, C, and D be integers, and B and D are not equal to 0. Therefore, A over B, comma, C over D are both elements of the rational number set. By definition, I suppose I should say. Okay, so now it says prove that the sum of 2 rational numbers is also a rational number. So let's now add them. So the sum equals A over B plus C over D. And in order to add these rational numbers, I need a common denominator. So it's going to be A over B and then times D over D plus C over D and then times B over B. And so when I'm done, I'm going to get AD plus BC over BD. And then I need to notice that AD plus BC is going to be an integer because, after all, A, B, C, and D individually were integers. So if I add or multiply, I get another integer. And also, BD is going to be an integer because, again, I took 2 integers and multiplied together. And BD itself is not going to equal 0 because B and D both were not equal to 0. So when I multiply them together, I can't get 0. Therefore, AD plus BC over BD is an element of Q by definition again. And that's what we're trying to show. When we add 2 rational numbers, we get another rational number. So that's our proof. The product of 3 consecutive integers is increased by the middle integer. Prove that the result is a perfect cubed. Well, first of all, we want to select 3 consecutive integers. So if I pick a letter for the first integer, let's say n, then the next one's going to be n plus 1 because they're consecutive, and the next one after that's going to be n plus 2. However, that may not be the most convenient version of this to do because I have to multiply n times n plus 1 times n plus 2 and then add on that middle integer. Instead, for symmetry's sake, I'm going to let n be the middle integer, and then the one right before it would have been n minus 1, and the one right after that would have been n plus 1. So selecting your arbitrary consecutive integers correctly or carefully might actually end up making the problem a little easier. So here's what I'm going to do. I'm going to let n minus 1, n plus 1 elements of z be the 3 consecutive integers. Now again, it had to be n minus 1, n, and n plus 1. They had to be adding 1 each time for them to be consecutive integers. That was not optional, but how you selected them was up to you. So first of all, we do n minus 1 times n plus 1, and then it says increased by the middle integer. Well, that means plus the middle integer, which was n. So now let's work this out. Well, I'm going to carefully multiply these two together, and then later on the n. So let's do n first, and then n minus 1, n plus 1, and then plus n. Well, that's going to be n times, and that's the difference of 2 squared, n squared minus 1, and then plus n. And so distribute that n, and it's n cubed minus n, and then plus n. And guess what? It's n cubed, which is a perfect cube. And that's the end of that one. Now, it would have worked the other way. I will write it out for you and let you briefly look at it without spending a lot of your time. So here's the slickest way to do it the other way. If you do n plus 1, n plus 2 are the 3 consecutive integers. So you have to multiply them n times n plus 1 times n plus 2, and then add on the middle integer, which is n plus 1. And then the slick way to figure this out is to factor n plus 1 out between this term and this complicated term over here, leaving you with n times n plus 2 and then plus 1. So n plus 2 and then plus 1. And then distributing it out to be n plus 1 times n squared plus 2n plus 1, and then recognizing that this is a binomial square, so this n plus 1 is still here, and this n squared plus 2n plus 1 is really n plus 1 quantity squared, and that becomes n plus 1 quantity cubed, which is a perfect cube. Now, if you didn't realize this shortcut, you would have to distribute combine like terms and then recognize that this is a perfect cube, which you could have done, but again, picking the integers to be these 3 just makes your life a whole lot easier. It's much less complicated of a process to do. So pick your choices carefully when you're doing things arbitrarily. And that's the end of the lesson.